In January 2022, Lockheed Martin announced that it had exceeded the annual production target for the F-35 fighter jets. It delivered 142 aircraft throughout the year, 3 more than the target of 139. It also announced that it would stably produce 156 aircraft each year starting from 2023 and onwards. Unfortunately, in July 2023, China, which has reserves accounting for 85% of the world's total and whose output accounts for 90% of the global total, announced the control of the export of gallium. This directly led the U.S. military to announce that it would stop accepting F-35 fighter jets just over 10 days later. Lockheed Martin only delivered 45 aircraft produced before July in 2023. And the F-35 fighter jets produced after that could only be stored in the factory in Fort Worth, Texas, waiting for upgrades in today's air combat. Beyond visual range air combat, which emphasizes detecting the enemy first, plays a crucial role. The radar of a fighter jet is of vital importance in beyond visual range air combat. The radar not only needs to conduct detection and tracking, but also serves as a data link transmitter to provide mid to long range air-to-air missiles with mid-course guidance. Whoever has a longer detection range will gain the upper hand in combat. As early as the 1960s, the U.S. F-14, a carrier-based fighter jet, was the first to start using the AWG-9 long-range radar. In order to gain a leading position, the Soviet Union developed the N007 Zr-Eslon flash-dance large passive phased array radar, which was twice the size of the AWG-9 radar. This radar had an average power of 2.5 kilowatts and a peak power of 10 kilowatts and could detect a cruise missile with a radar cross-section of 0.3 square meters at a distance of 65 kilometers. The JAPG-1 active phased array radar on Japan's F-2 fighter jet was the world's first mass-produced gallium arsenide transceiver TR module active phased array radar. Subsequently, the United States developed the APG-77 active phased array radar for the F-22 fighter jet, which had the highest power among airborne radars at that time, with a peak transmit power of 12 kilowatts. The principle of radar is that by transmitting radio pulses towards a target and being able to receive the energy waves reflected back, the distance, speed, and direction of movement of the target can be detected. In the past, radars changed the antenna mechanically to detect specific areas, and only one area could be detected at a time. A passive phased array radar has only one main transmitter, and the antenna itself cannot generate radar waves. However, the APG-77 active phased array radar consists of two 000 transmit and receive TR module components. One TR component is equivalent to a small radar, which is embedded in a flat panel antenna one by one. There are no moving parts, and it can still operate normally, even if one or more components fail. The radio pulses generated synchronously can be switched between targets in real time, allowing it to monitor other areas while tracking a target, since it is not necessary to rotate the antenna when scanning different directions. The data update rate has been improved from the second level to the Micros Econ D level, which is a major breakthrough in the field of airborne radars. Since the emergence of active phased array radars, they have become the trendsetter for the development of airborne radars. In the past decade or so, the United States has developed the APG-79 active phased array radar for the FA-18EF Block II fighter jets, the APG-80 active phased array radar for the F-16EF Block 60 fighter jets, the APG-63 V2 active phased array radar for the F-15C fighter jets, and the APG-81 active phased array radar for the F-35 fighter jets. Facing the flood of active phased array radars from the United States, Russia has been unable to develop its own active phased array radar. Russia developed the ZHUK-ME active phased array radar for the MiG-35 fighter jet. However, Russia has been unable to produce gallium arsenide transistors and could only buy some civilian gallium arsenide transistors that are nearly 100 times larger in volume on the international market. Therefore, Russia's new Su-35S fighter jets and T-50 fighter jets can only use the Irbisi passive phased array radar to increase the detection range. It can only strengthen the power of the transmitter. When the limit is reached, electrical arcing will occur, and the failure rate will increase significantly. Back in the day, after China introduced the pulse search radar with a short operating range and poor detection effect from the Soviet Union, it stagnated for nearly 40 years. In the early 1980s, it was still begging to introduce the innate PG-66 pulse Doppler radar of the U.S. F-16 fighter jet. It was not until the early 1990s that a prototype of the pulse Doppler radar was developed. After that, it only took a short 5 years to achieve a technological leap from a single pulse system to a full waveform pulse Doppler system. It took another 10 years to comprehensively apply the pulse Doppler fire control radar. Since then, the design and production technical difficulties of the pulse Doppler radar with a flat plate slotted array antenna have been solved. In 1996, the research on passive phased array radars began. It only took 8 years to pass the acceptance of the results. In 2002, the research on passive phased array radars started. Foreign radar experts were confident that the cost of China's TR modules was quite high, probably 3 times the affordability of customers, and that the phased array radar could not be simply assembled like Lego building blocks. The TR module is a key component of the phased array radar. The quantity and power determine the performance of the radar. The first generation TR modules use elements such as silicon and germanium as semiconductor materials, with a band gap of 1.1 of electron volts. The second generation TR modules use gallium arsenide as a semiconductor material, with a band gap of 1.4 eV. The third generation TR modules use gallium nitride as a semiconductor material, with a band gap of 3.4 eV. The wider the band gap, the greater the energy required for valence electrons to break free and become free electrons. Gallium arsenide is very sensitive to temperature, and the spacing between each transceiver module is close, resulting in ineffective heat dissipation during operation. Liquid cooling can only be used to cool the antenna array. Gallium nitride has the advantages of high voltage, high speed, high power, high efficiency, and high temperature resistance. It can withstand higher voltages, has a higher output energy density, and can operate at a higher ambient temperature without changing the antenna size, aperture, and total power. The detection range can be doubled. The TR module of the PG-77 active phased array radar on the F-22 fighter jet is like a brick, and the cost of one TR module reaches $600–800 US. The TR module of the PG-81 active phased array radar used on the F-35 fighter jet is as thin as a tile, and the cost is reduced to around $200 US. Gallium nitride represents the greatest performance leap in the history of active phased array radar technology. Previously, the active phased array radar technology has been limited by the fact that the transmit power of the gallium arsenide TR module is only to 5 watts, while the gallium nitride TR module can provide a transmit power of up to 50 watts, which is 10 times that of the gallium arsenide TR module. The efficiency of the gallium arsenide TR module is only 30%, and the efficiency of the gallium nitride TR module can reach 48%. If each gallium nitride TR module can continuously provide 40 watts of microwave energy, and the power increase efficiency can reach 50%, the peak power can reach 60 kilowatts. China successfully developed a gallium nitride TR module with a transmit power of 119 watts in 2008. The APG-79V for active phased array radar of the F/A-18 Hornet fighter jet is the first gallium nitride active phased array radar of the U.S. Air Force. The AN/SPY-6 Aegis dual-band active phased array radar, an MPQ-65 a Patriot air defense and anti-missile radar, and TPY for active phased array radar also use gallium nitride TR modules. The APG-81 active phased array radar used on the F-35 fighter jet is developed from the APG-77 radar. When detecting in the air, it can detect a target with a size of 1 square meter at a distance of 150 kilometers. And the maximum detection range is 180 kilometers. In the Atlantic Trident exercise in August 2017, the F-22 and F-35 of the U.S. Air Force played as the blue team, and the Typhoon fighter jets of the UK and the Rafale fighter jets of France played as the red team. In the exercise, the F-35 achieved remarkable results. The Typhoon fighter jets and the Rafale fighter jets could not detect the signal of the APG-81 active phased array radar at all. After being locked, they were shot down without any awareness and didn't even know where the missile came from. They couldn't get into the close combat range at all, and the combat loss ratio was 0.19. And for the Rafale fighter jets it was 0.18. However, the U.S. military is very dissatisfied with the performance of the APG-81 active phased array radar because it still uses gallium arsenide TR modules and its performance is no longer advanced. Chinese fighter jets such as J-35, J-20B, and J-20S all adopt gallium nitride TR modules. The early J-20 fighter jet has 856 gallium arsenide TR modules, and can detect a target with a size of 1 square meter at a distance of 187 to 127 kilometers, which is comparable to the F-22 fighter jet with 956 gallium arsenide TR modules. The latest upgraded version has 200 gallium nitride TR modules. Even the J-16 and J-15T fighter jets are equipped with 200 gallium nitride TR modules and can detect targets for 500 kilometers away. The antenna gain is as high as 60 decibels, completely unaffected by any electronic interference. Moreover, a key technology is adopted that can control the output of the radar beam to a power sufficient to lock onto the target, distributing the flat pulse simultaneously over every frequency in the instantaneous bandwidth of the radar and compiling the broadband radiation into pseudo-clutter, causing the ALR-90 and ASQ-239 electronic reconnaissance equipment of the F-22 and F-35 to have no response to the search of this radar, which is a terrifying phenomenon. The U.S. military has clearly realized that it must upgrade the active phased array radar of the F-35 fighter jet as soon as possible. That is, the APG-85 active phased array radar designed by Grumman. If the F-35 fighter jet is equipped with an APG-85 active phased array radar, the detection range can be increased by more than 1.7 times. This radar can be compatible with all models of the F-35 ABC fighter jets, but it will only be installed on the Block 4 version of the F-35 ABC fighter jets. The over 1,000 F-35 fighter jets produced previously cannot be retrofitted. Northrop Grumman started developing it in January 2023. It is expected that the 7 F-35 fighter jets of the 17th batch, which will start delivery at the end of 2025 or the beginning of 2026, can be equipped before the end of 2025. The newly produced F-35 fighter jets need to undergo TR-3 hardware upgrades, upgrade the computer that can store and process more data, improve electronic warfare and search, tracking, target identification, and engagement capabilities, and prepare the foundation for equipping the Block 4 version with the under development and APG-85 active phased array radar. The main upgrade of the NAPG-85 active phased array radar is to use gallium nitride TR modules to increase the detection range and resolution. Besides using gallium nitride TR modules, the computing power of the computer corresponding to the Block 4 version of the radar must also be upgraded by 25 times. However, the NAPG-85 active phased array radar has high power and consumes more electricity. And the power generation of the F-135 engine used by the F-35 fighter jet cannot meet the power required for the normal operation of the NAPG-85 active phased array radar. The U.S. military launched a tender in 2016, and both General Dynamics and Pratt & Whitney obtained research and development contracts. General Dynamics one is called XA-100, with a thrust of 200 kN, and will be completed as early as 2027. Pratt & Whitney's one is called XA-101 and is expected to be developed and completed around 2027-2029. After being equipped with the NAPG-85 radar and the Block 4.1 upgrade version, the F-35 fighter jet can detect the Typhoon fighter jet at a distance of 230 kilometers and launch the AIM-120D missile to attack at a distance of 150 kilometers. Moreover, the Block 4.1 upgrade version enables the back-end data of the NAPG-85 active phased array radars of several F-35 fighter jets to be processed integrally. Each F-35 fighter jet in this network is a transceiver node, so it can be integrated into a multi-static radar composed of software virtualized ion. The battlefield situation awareness is equivalent to that of a traditional early warning aircraft, and the entire battlefield can be clearly seen. It can also enable each fighter jet in the team to have the same situation awareness ability. Due to its stealthiness, the F-35 fighter jet can continuously scan the space and perform 3D modeling in the theater at will, and transmit detailed regional images back. Non-stealth aircraft provide firepower support for the F-35 fighter jet in the rear. When the opponent tries to attack the non-stealth aircraft, it is difficult to find that they have already been detected by the F-35 fighter jet and the data has been transmitted to the non-stealth aircraft. The non-stealth aircraft can directly launch air-to-air missiles to form several firepower interception nets, with the F-35 fighter jet guiding in the front, and finally achieve remarkable combat results. Unfortunately, this dream was completely shattered after China announced the control of the export of gallium. The F-35 fighter jet has no hope of obtaining gallium nitride TR modules, and even the production of gallium arsenide TR modules has become impossible. The total number of orders for the F-35 fighter jet is 320. Coupled with other radars, a huge amount of gallium is needed. In contrast, China, which has the largest amount of gallium in the world, doesn't have to worry about a shortage of gallium at all and can sell it at a low price. The KJL-7A airborne active phased array radar for export by the China Electronics Technology Group has an antenna outer diameter of only about 600-700 millimeters and is equipped with just over 1,000 gallium arsenide TR modules. It has the same 11 working modes as the NAPG-81 active phased array radar and a detection range of 170 kilometers, which is no worse than the NAPG-81 active phased array radar at all. One unit costs only $3 million, while one NAPG-81 active phased array radar costs as much as $10 million. And that's for the US military's own use. Of course, without gallium, indium phosphide, silicon carbide, aluminum nitride, zinc oxide, and diamond can also be used as materials for TR modules. But their performances are all inferior to that of gallium nitride. It is estimated that within 10 years, the F-35 fighter jet will not only be unable to compete with the J-20 fighter jet, but also have problems competing with the J-35 fighter jet. The J-35 fighter jet has better stealth performance than the F-35 fighter jet, and its flight speed and maneuverability are also stronger than those of the F-35 fighter jet. The active phased array radar used by the J-35 fighter jet can be equipped with 600 gallium nitride TR components. And it clearly Harcraft can directly launch air-to-air missiles to form several firepower interception nets, with the F-35 fighter jet guiding in the front, and finally achieve remarkable combat results. Unfortunately, this dream was completely shattered after China announced the control of the export of gallium. The F-35 fighter jet has no hope of obtaining gallium nitride TR modules, and even the production of gallium arsenide TR modules has become impossible. The total number of orders for the F-35 fighter jet is 320. Coupled with other radars, a huge amount of gallium is needed. In contrast, China, which has the largest amount of gallium in the world, doesn't have to worry about a shortage of gallium at all and can sell it at a low price. The KJL-7A Airborne Active Phased Array Radar for export by the China Electronics Technology Group has an antenna UTER diameter of only about 600-700 millimeters and is equipped with just over 1,000 gallium arsenide TR modules. It has the same 11 working modes as the NAPG-81 Active Phased Array Radar and a detection range of 170 kilometers, which is no worse than the NAPG-81 Active Phased Array Radar at all. One unit costs only $3 million, while one NAPG-81 Active Phased Array Radar costs as much as $10 million. And that's for the US military's own use. Of course, without gallium, indium phosphide, silicon carbide, aluminum nitride, zinc oxide, and diamond can also be used as materials for TR modules. But their performances are all inferior to that of gallium nitride. It is estimated that within 10 years, the F-35 fighter jet will not only be unable to compete with the J-20 fighter jet, but also have problems competing with the J-35 fighter jet. The J-35 fighter jet has better stealth performance than the F-35 fighter jet, and its flight speed and maneuverability are also stronger than those of the F-35 fighter jet. The active phased array radar used by the J-35 fighter jet can be equipped with 600 gallium nitride TR components, and it clearly has the upper hand and a dominant advantage in radar performance. China's rapid progress is not only beyond the reach of the United States, but also that of the whole world. Sweden's Gripen fighter jet's upgraded PS-05A Mk5 NORA active phased array radar has been unable to make progress in TR module technology. It sought help from the United States and France, but was rejected in the end. Russia is still struggling with the N-035 Irbisi passive phased array radar, while the US NAPG-85 active phased array radar is still a long way off. China's next-generation gallium oxide TR modules have also begun to enter the practical stage. The United States has already fallen behind by 20 years.